Good morning, everyone. My name is Lauren McNamara, and thank you for joining Horizon Solutions Let's Get Motoring with AC Motors, hosted by Kevin Beach and Scott Savage. We'll get started shortly. We do have a large audience registered today, so to avoid any background noise, we have muted all mics. If at any time you have a question during the webinar, go ahead and submit that over in the Q&A feature at the bottom of your screen, and we'll get those questions answered at the end of the presentation. This webinar will be recorded and distributed to everyone once we have concluded. With that said, let's get into the webinar.
Well, good morning, everyone. Thank you for joining us. My name is Kevin Beach. I am the Power Control Automation Specialist for Horizon Solutions Central Region. And in that capacity, I support our clients in Western Massachusetts, Eastern New York, and the state of Vermont.
And I'm Scott Savage. I'm the Power Control Specialist for the East Region, Maine and New Hampshire, and also cover Western New York, Elmira, Rochester area.
So a rough look at today's agenda is we're going to do a little primer on AC induction motor basics, just to make sure everybody is kind of on the same page. You know, how did they come around to exist? How do they work? The thing that's going to permeate through the whole presentation today is the concerns when using an AC motor with a VFD, and that includes reflective wave. And we're going to talk about the NEMA MG1 standard for motors. Scott's going to get into a bit on the motor performance, and we're also going to talk about the optional motor technology that's available today. And then we're going to talk about selecting the proper bearings for your motor based upon how the load is coupled and some other factors. Okay, run through a quick bit of history here. Back in the early 19th century, a French physicist hypothesized about the existence of rotating magnetic fields. 1879, Walter Bailey sat there switching things on and off, and he actually got some magnets to follow that rotating magnetic field. A few years later, Galileo, Ferraris, and Nikola Tesla independently created the commutator-free AC induction motor, and what that meant is nobody had to sit there flipping switches. Tesla applied for a bunch of patents, and he got some of them. George Westinghouse licensed those patents that he received, and he purchased the U.S. option for Ferraris's design. A couple of years later, GE started developing their own AC induction motor and signed an agreement with Westinghouse for something called the bar winding rotor design. Today, we know this as the squirrel cage rotor. And just a point of reference, back in 1897, a 7.5 horsepower was pretty big, roughly the size of a modern 100 horsepower motor. So here is the squirrel cage design. I can actually, in my mind, I can actually see a mouse or gerbil running around, I think, spinning it around. In the center, you would see the laminations, they call them, that are on this, and they are the magnets that are going to be on this rotor. And here's a cutaway showing it. There's the rotor spinning. That's the go roundy part. And here's the stator. That's the stationary parts on the outside of the windings of the motor. If we continue on, here's a cutaway of this. And there's the rotor. And if you look closely at the rotor, you can see the laminations on that and those are the magnets. Here's the stator, and I can't get my cursor to show on this, but on the sides of the stator, top and bottom, you can see all those wires there. Those are what we call the windings. And that is what creates that rotating magnetic field. And it goes around like this. A couple other parts of the motor here is the shaft. That's obviously where the load is coupled. I'm going to show you the bearings. We're all, don't mean to insult your intelligence, but I just want to point those out because we are going to talk about these a bit. Then on the back of this particular motor, there's a fan that's attached to that shaft, the rotor shaft, and then there's some fins on the housing. And depending on the rotation of the motor, that fan is either going to push or pull air across those fins to cool the motor. It's called a totally enclosed fan cooled motor, or TEFC. So this brings us to the first VFD gotcha. And you got to be able to keep this motor cool. So when you're looking at a totally enclosed fan cooled motor, you need to take the cube law into consideration. What that means is as the speed goes down of the motor, the air passing over those fins drops by the cube of the speed. In other words, a 1750 base RPM motor running at half speed or 875 RPM is getting 1/2 cubed or 1/8 the flow of air over over those fins. So you can see it's really going to be a cooling problem. And this really applies when you're using a VFD on this. What do? We can add an external blower to it. That's called totally enclosed blower cooled, or TEBC. And I'm trying to get it so you can get my cursor out here. Let me see if it works now. And it does not. But anyways, on the top of this motor, you can see the external blower, and you can see the motor attached to it. That means the cooling fan has its own motor, and it's not attached to the rotor, so the cooling is not dependent on the motor speed. It typically would use ambient air in the room, but sometimes that supply is piped in from the outside, and that would attach that little round fan or frame you see on that blower. That is, where would you use that? You use that in something that's got a high ambience, such as a foundry or a steel mill, or in the basement of a paper mill where it gets very hot. You'll bring that in from the outside. It's important to remember that in most cases, a separate motor starter will be needed to start that blower motor. It typically will not start automatically. This design is called a piggyback motor. There's also a piggyback blower. There's also a design called axial, which would stick off the back side of this motor in line with the shaft that you see in the picture. Another way to do this is called totally enclosed non-ventilated, or TENV. The motor, in this case, has no cooling fan at all, but uses the insulation of the motor to cool itself. Again, the cooling of the motor is not dependent upon the speed of the motor, but the motor may still have fins to aid in the cooling. Now, the motor you see here is a Marathon Blue Max motor, which is inverter duty motor, designed to go with a VFD, and it has fins, even though there's no fan on this. The fins aid in the cooling. I also suspect it cuts down on the number of castings the motor company has to buy for a particular frame size. And they typically have a higher speed range than TFC, but that's not necessarily the case. So you got to look at it, which this now brings us to VFD gotcha number 2. Watch the speed range. So what we're looking at here is another Marathon Blue Max motor, 40 horsepower, 1750 RPM, and it's 2,000 to 1 speed range. That means this guy can run down to like 1 RPM and sit there, run like that all day long. Don't recommend it. There's more efficient ways to do those things, but it is possible. Here is a Marathon Blue Chip motor. Now, this is a typical industrial motor that you would find. The one on the top is, as I said, it's an inverted rated motor. The one on the bottom is what we would call VFD ready. What's the difference? Well, it's this. This has a 2 to 1 speed range, which means that if you run this thing at 700 RPM, this motor will overheat. And that's really the difference between inverter designed motors and inverter ready motors. If you look at the data sheet for the top motor, the Blue Max motor, it's actually going to say in starter mode, it's going to say VFD only. You can start it with a motor starter, but why spend the extra money for something like that if you're just going to run it at base speed? The bottom one is rated for either starter or VFD. We hear the term 6-pole, 4-pole, 8-pole motor. So what is a pole and what difference do they make? Well, poles refer to the number of magnets on the rotor, and they dictate the base speed. 2 poles, 3,600, 4 is 18, 6 is 12, 8 is 900. Are there other slower motors? You bet. Paper industry is going very heavy into higher pole count, slower speed motors, because what it does is it allows them to eliminate the mechanical transmission on it and direct couple the motor to the load and avoid the weakness of a gearbox or things like that. For those of you who ski, modern ski lifts are now coming with direct drive motors for that exact reason. The motor's much bigger, much more expensive, but the big weak point in the mechanical transmission is eliminated. So on the right, you see a 4-pole motor. You see the 4 magnets rotating with the rotor, and the colored bars on the outside are the stator, or the windings where the rotating magnetic field is generated, like that. And the magnets chase that. They follow it around. Now, the most common motors we see are called AC asynchronous motors, which means there is motor slip, which is a little bit of lag on the rotors, on the rotor magnets behind that rotating magnetic field. It's normal. That's how an AC asynchronous motor works. There's something called a synchronous motor where it doesn't do that, but that's not a basis for that's not part of the topics for today, and it's a whole different subject. Higher number of poles and lower base speed provides more torque. And what do we mean by that? 4-pole typically delivers 3 foot-pounds per horsepower. 6 gives 4.5. 8 gives 6. If I had a 2-pole on here, you would see it's 1.5. It's very linear. And we're talking about little differences things make a difference here. Let's take a look at the voltage. 575. Scott's going to talk about efficiencies and savings. So we're looking at 575. It draws 1 amp per horsepower. 460, 1.25, and 230 is 2.5. And you can see that's pretty linear right there as well. And this brings us to polling question number 1.
Yes, it's time for our first poll. So I will launch the poll. And we are looking to know, what is the percentage of MG1 motors you have in your plant? Your options are 25% or less, 50 to 75%, or 75% or more. And we'll just give everybody a couple of seconds to get those votes in. So I'm going to close the poll and share the results.
Well, it's a good thing. Looking at these percentages, I think it's a good thing everybody's here.
I agree. Well, thank you, Kevin. Thank you, Lauren. Let's get into why the MG rating evolved. In about 1987, after the advent of the first IGBT technology was released, NEMA decided to do an MG1 rating. Some of the reasons for that, these drives have non-sinusoidal waveforms. With pulse width modulation and some of the effects that happen with these fast switching drives, we have increased motor losses, like Kevin talked about before, with the inadequate ventilation of these lower speeds. A lot of dielectric stress at the windings on the motors, and we have a lot of noise, basically in the shaft currents, and something that we need to pay attention to. In one of our webinars previously, we discussed a lot of grounding procedures that we'd like to see with the motors to the drives. So feel free to go back and watch that recorded webinar if you did not see it. All these combinations, with the motor's insulation and the bearings, severely shorten the life of the operating life of a motor. One of the reasons is the high switching rates on these power transistors, the advent of the IGBT, insulated gate bipolar transistor, added a lot of shortened switch times, where the DVDT was rather steep, where we had a huge change in voltage over a very, very short period of time. And this caused a lot of issues with steep fronted waves that would go down to the drives. So basically, MG1 was brought on to address some of those issues. Motors were burning up all over the place. Motor manufacturers were pointing fingers at drive manufacturers, and the problem really wasn't resolved until MG1 took effect. About the time in the early 90s to mid 90s, we started to see the IGBTs definitely come into the marketplace, and basically they were predominant over their predecessors. Also, things to consider were with these short switch times were the longer motor cable lengths. And sometimes with these extreme motor cable lengths, you're talking out over 1,000 feet, you would see voltages go as high periodically, as high as 2150 volts. This is very, very interesting because, at a 10% over voltage on your drive, and saying your voltage is higher going and being rectified into the drive, you're going to see higher switching values. So it's also important to try to keep your voltage on your VFD down near the nominal rating of 480 volts. So we sort of look at this and we say, all right, I'm going to send it out and get my motor evaluated by an ESA shop, and they come back and they tell me that I've got a phase-to-phase short. And it's basically because of all the insulation breakdown that's happened due to some of the mismatches in an impedance. Next slide. So let's just take a peek here, right? As Kevin talked about, we've got, a low voltage winding. We've pulled out the rotor so you can see the stator. MG1 Part 31 standard requires that these windings are able to withstand 1600 peak volts. Basically, a 460 volt motor, we'll just take that as an example. Nominal peaks that you see are usually about 3.1 times the 480 volts that is being introduced onto the drive. Also, this comes into play with the short rise times. You're down at 0.1 microseconds for rise times with these IGBTs. Next slide. We talk a lot about CIV ratings in some of our technical documents. These are the voltages that are required above and beyond those ratings, right? The ratings where corona will occur. And corona basically is a bubbling effect. It makes voids in the resin on the windings. And once those corona bubbles line up, it will start to cause shorts phase to phase or even phase to ground, which will lead to ground faults and also high current ratings prior to the drive failing on a ground fault. MG1 states that the CIV rating is at 1600 volts so that we do not exceed that rating. Most of the time you'll see that 460 volt motors will see that 3.1 times the voltage coming into the drive, and that will be about 1426 volts. So we are down below the CIV rating, therefore the windings will be able to withstand the rough waveform that's coming in. Just keep in mind too, if you do have 575 in your plant, you might want to check with your manufacturers. 575 reflected wave becomes more predominant as the voltage goes up and the lead lengths go out to the motor. Next slide. Now let's just switch gears here a little bit and talk a little bit about premium and standard ratings on motors. And here's some of the efficiencies. And I know this is a busy chart, but just for example, you'll see that as you go from the lower horsepowers to the higher horsepowers, you're going to see the impedance on the stator is going to decrease. Therefore, it is increasing the efficiency of the motor, whether it be a standard or a premium efficient motor. But you can also see that if you reduce the amount of standard efficiency motors you have in your plant, you can increase your efficiency tremendously. Whether you're running across the line with a motor starter or with a VFD, there's a definite increase. And you can see it's about $250 a year for the 10 horsepower unit. You'll also see that, let's just take an example, at 75% load, all these tests are done, and these are the percentages of them. You'll see in the premium efficient area that you do go up from a rating of around 92% efficiency to 96. So, you know, replacing these motors and not giving your money away to the electric company probably is a wise idea. There's also programs out there in many states where you can get a prescription and get X amount of money off each motor to go from a standard efficiency motor to a premium efficient motor. We want to use less electricity and build fewer generation plants is the goal with those programs. Next slide. And let's take a look at different loads, right? That testing that is done by the Department of Energy is always done at 75% load, but you'll see, let's just take, for example, let's take the 200 horsepower unit. At full load and at 75% load, you're at 96%. Now, a drive will operate 98% at full load and approximately 95% at half speed. So you can see this lines up very well with energy loss, because you're not going from one device and losing X amount and then going to the next and losing more. They're pretty much predominantly in the same ballpark now. The approach that a premium efficient motor is less robust than a standard motor is not true. They are as robust, if not better, especially when you have the MG1 rating, because they have to meet that. So over the years, when it began in 1987, and then it went all the way through, you can see that the technology of the drives especially has increased, and the motors and the build of these motors has definitely increased and become more robust with the MG1. Next slide. Let's take a look at temperature ratings. You know, when we look at the nameplates on these motors, we say, well, it's just a nameplate. I only need it when I need to replace the motor. Well, you sort of need it for other reasons too, right? You want to make sure that the application and the ambient temperature that you're putting these into lines up with the insulation rating. So what we've got is different alphabetical ratings for these temperature ratings to withstand more heat and not melt down and cause shorting inside the windings. So we basically say, especially with VFDs, we prefer an F rating or above. Just because we have, you know, more temperature, hotspots, etc., in the drive, especially like on the end turns of the motor, which you'll see in another slide here coming up. And this just helps to withstand not only the waveform, the rough waveform, but also the high temperature that may occur. A high temperature rating of H in ovens, etc., should be considered to going from an F to an H if the ambient elevates, and those are good for 180 degrees C. So please, when you're, you know, adding a VFD to these motors, consider this also, as well as you know, the MG rating. Next slide. Here's something Kevin and I get asked a lot. You know, I'm looking at the nameplate. I really don't know what I'm looking at. Let's take, for an example, the RPM 1750 here. And now we're going to look at this and we're going to say, okay, I do meet the Class F. That's great. So now I have a standard 4-pole motor with 50 RPM slip. I'm rated for the 155 degree temperature. And now let's look at this. I always get asked this question, and especially people that are not really familiar with the motor design of the induction motor. This is on an induction motor only. This excludes some of the slides we have coming up with permanent magnet motors and switch reluctance motors. But basically what we're showing here is we have constant torque out to base speed. And you can see the red line goes down. Base speed is 60 Hertz, right? It's what the full RPM of the motor is at 60 Hertz, and that would be line frequency. So if you were running a drive, you would have constant torque or high torque levels all the way up to 60 hertz. But what happens after you go past base speed? Well, you can see by the chart here, the torque decreases. Because horsepower is equal to torque times RPM divided by 5252. So we have a constant horsepower situation above 60 hertz. So say you want to go 70, 80 hertz. What is the limitation? Well, you can see by the red line that's drawn here, we're out at 90 hertz. That basically is the limit where the torque drops off with a Tesla design motor at 90 hertz, and then you're in some serious problems because you've gained it all in RPM and you've lost it all in torque. So all the physical attributes and mechanical attributes of the motor definitely hold true here. So be very, very careful here. It's very important when you overspeed to make sure that you have enough torque. Next slide. Let's take a look at it again, right? And from the electrical point of view of this, it would be the volts times amps divided by the 1.73, right? Would give you the kilowatts. This is the mechanical equivalent of it, right? RPM times torque equals, divided by 52 equals horsepower. So let's see what we're doing here. This would be if it was on a drive. Notice again, the fuchsia lettering across the top shows constant torque. But look at the power in the green line that goes up. Basically what we're doing with the drive is we're changing the voltage. So as we increase the voltage, we increase the power, but we're giving you full torque. Okay, and torque is synonymous to a volts per hertz ratio, correct? So as we increase up in power and we're giving you constant torque, that is the rule for base speed with the red line going vertical and to the left and down. When we do above base speed, you can see we're into a field weakening situation. Some of you old DC guys remember we used to lose control of the motor if we weakened the field too much because we were overspeeding. This doesn't really happen with the technology we have today with AC drives. We never lose control. We take a lot of precautions on that because we're very leery of what happens over base speed with the motor. Notice how much the torque decreases. So once again, just be extremely cautious when you're going over base speed. Next slide.
So it's time for our second poll question. The question is, what percentage of motors in your plant are run on VFDs? You have 0 to 25% or less, 50 to 75%, or 75% or more. And I'll give everybody a couple of seconds to get those votes in. We still have some trickling in. All right. So I closed the poll and shared the results.
Well, that's interesting. That's kind of exactly where I expected to see it drop in.
There definitely has been a huge increase in VFDs on motors in the last 15 years. Thank you, Lauren. You always do a great job. I don't know if you'll be doing many more of them for us, but we really appreciate you as a panelist. Let's move on to different types of motors for this technology. We have the induction motor, which people are probably very familiar with, maybe not, and I'm really pleased if you're here and you don't know much about induction motors. You're probably learning quite a bit. But we also have other motors that we drive with VFDs. A lot of our customers don't realize this, but you can definitely reduce your losses using permanent magnet motors or switch reluctance motors. Both are actually able to be tunable with our VFDs. We also have a list in the back of our manuals, in the 750 manual, that gives you some great suggestions for permanent magnet motors. It's in one of the appendix. But basically, when you've got a permanent magnet motor, you've got motors inside. These are your magnets, like Kevin talked about, that were the magnets on the laminations on the induction motor. And now we're going to use these magnets, and they're going to mount inside the motor, and we will use those for the attraction. These are usually a permanent magnet motor technology. They're limited in size, but they give you great instantaneous torque, and they give you really good efficiency. So the other one is the synchronous reluctance motor. That's where the magnets are embedded into the iron, and they're not just a permanent magnet that's mounted out to the side. That's more of a coil structure around the iron. And they're used a lot in Europe, very predominant, not so much in North America. And they're used in North America right now, mostly in the automotive industry. You'll probably see more applications where they're showing up just because of their efficiency. Next slide. And here's just want to caution everybody about permanent magnet motors. Remember, the rotor has the permanent magnets on them, and if it's rotating, if the shaft is rotating at all, even if it's locked and tagged out at the drive, for example, there will be voltage present at the leads, and it's a safety issue. So please be careful out there. Next slide. And now we look at the switch reluctance, right? Came out, the concept of it came about the time when the switching phenomenon was done by Arago, right? Way back. This was another style of motor they came out with. You can see that the magnets are embedded on the stator on the outside. A little bit different than the laminations that we had on the induction motor. You can see the time frame when it pretty much came about. But one of the exciting things about this is, in the mid 1960s, there was some more development, and with the advent of the MOSFET, and especially the IGBT that came out in the 90s, this actually pushed the development even further with these type of drives and motors. Next slide. Now let's change gears here a little bit, and we're looking at noise. So versus reflected wave, high frequency noise is also bad for the drive, for the motor. And instead of a winding issue where you have over voltages, battering on the end turns of the motors, you also have you have high frequency noise that is emitted by the drive. Remember, the carrier frequency of these drives is between 2 and 10 kilohertz. And what happens is you get a lot of circulating currents that go up and down the cable, especially if you don't use VFD cable. This becomes more of an issue. It becomes more predominant. So all these circulating currents are going all over the place in the kilohertz range. Well, what happens is you start to get fluting. And that fluting is on that race where the red arrow is. That fluting becomes a repeated pattern. And then you end up getting chattering in your bearings, and eventually failure. The other thing that happens with this is it also circulates through the ball bearings or the roller bearings, and it causes a frosting effect. And that actually adds to the degradation of the motor also. A really quick fix to do this is, when you order a motor, or you can retrofit it afterwards, is use the Aegis rings. The brush will make contact with the shaft, and then it will release those high frequency currents back out to the chassis and allow what we're going to show you here in a second on a simulation with circulation on the shaft. Next slide. Remember, capacitive currents get extremely different depending on the size of the motor, the shape of the motor. So you can see when you get it up into high output machines, there's more of a chance of induced shaft voltage. And that gets very expensive. Large motors cost big money. Also, the physical shape of the motor. The shorter and the more round in diameter that it is, the more better it is to reduce the amount of capacitive currents. The long, thin motor design, just be careful. That adds a little bit more to the capacitive currents situation. High pole counts that Kevin talked about earlier, those actually work in your favor. So if you can use a 1200 RPM or a 900 RPM motor instead of a 1750 RPM motor, that works to your advantage. Remember, running at low speeds, increases bearing temperatures, obviously, especially with heavy loads and not turning as much, and it thins out the lubricant film, and it's just something to be aware of with capacitive currents. Next. Okay, up on the left, this is what we call the ringing effect. So as the transistor is unsaturated, you get a greater overshoot, and then it settles in. So every time, not every time, but predominantly, every time you switch from positive to negative on the sinusoidal simulation of the waveform, you're going to get some overshoot. So IGBTs are notorious for this. It's just the way the transistor is manufactured. Versus the first generation GTOs and the BJTs, they were much slower switching devices. We've got concerns with the rapid voltage change again. And now we're referring to reflected wave. So the two phenomenons you have are your noise or your capacitive currents that you have to deal with the motor, and you have to deal with the reflected wave that will cause issues that you see. It's showing this picture on the right with the red arrow, where this just punched a hole through the end turns of the motor. The corona built up, it got across there, then you got a short, then you lost your insulation, then you lost your motor. The only choice you have here is to send it out to an ASA shop and get them to rebuild this or buy a new motor. A lot of manufacturers nowadays, 50 horsepower and under, they're just replacing the motor with a new motor. Next slide. We want to really, really prevent this from happening. So it's just MG1 helps us with this situation. I'm showing you a lap winding over here on the left versus a concentric winding or a machine winding on the right. The lap winding, and here's a little bit of a plug for Tech Top. That's another brand that we sell besides Marathon. When these are this lap winding effect is the conductors inside the winding actually are more consistent. It leads to less problems with reflected wave and issues like that. Also, another thing that I strongly suggest with some of these motors that helps is vacuum impregnated process, where when they dip these, they have a vacuum procedure that they use. It allows the resin to get into the windings, especially when they're strung in a ordered manner versus the concentric winding effect. These two things add to a better, higher quality motor. Also, another thing that they do, and I don't know if you ever asked this from your motor manufacturer, they do a lot with antimicrobial coating that they apply also on the resin to help in situations where you have mold or bacteria. Next slide. All right, and once again with the MG rating, please look at like part 30 and like part 31. They get into voltage ratings. I won't really get into it too much, but once again, you can see it's the volts and the amount of microseconds it takes to switch and get to the maximum voltage. So those are the two factors that you have to worry about when you're dealing with a motor manufacturer and you're trying to hold the MG1 rating. Obviously, if you have the MG1 rating and it's inverted duty rated for the MG1, that's better than some of the other sinusoidal motors that in the past people have used on VFDs. Next. So when you're running at extremely low speeds and constant torque, just be careful. Make sure you're using a higher quality motor. Going over base speed also, higher quality motor. It really, really helps. All right, and then inverted duty motor, just make sure you refer to, part 31, where it refers to the definite purpose inverter fed polyphase motors. right? And that's another section that I strongly recommend that you look at. And these are all published by NEMA. You can grab them off the web. It's a great resource just to understand how they make a true inverted duty motor. Next slide. And here we go. Here's a good example that you've probably physically seen on the news. It's sad news, but you know, basically when you have a tsunami, right? Boulder falls over in the the cliffs of Chile, and starts a reflection across the Pacific Ocean. You have a long lead length with no impedance, and then it hits the beach. That's exactly what's happening when you're emitting from a VFD down the cabling. And remember, it's very important, the physical attributes of your cable, because when you have cabling where you may have put them in conduit, or you may have, when they're physically separated, it causes a lot of capacitance. You want to reduce the amount of capacitance in your cable so that when it gets to the motor and you've got an MG1 rated motor, you don't have an impedance mismatch. And remember, that's that 3.1 that I talked about, 1426 peak volts on a 460 volt system. And we definitely want that above 0.1 microseconds. That can cause issues too, because the faster the rise time and the higher the voltage overshoots means the more damage that'll take place down at the end turns of the motor. Just switching gears here really quick, going to a medium voltage inverter motor. Okay, versus the base ratings, that's 600 volts and above. So typically in North America, 2400 volts and 4160 volts. You're going to see that the motors need to withstand 2.04 times the line-to-line rating. And the rise times are a little slower now, right? They must equal or exceed 1 microsecond. So we've got a little bit of breathing space there with the medium voltage. Next slide. We all get asked this question a lot as VFD specialists. Hey, I've got a 230 volt or a 208 system, and I'm worried about reflected wave. Well, the motor construction for the MG1 motors is rated for the 460 volt motor standards. So this is not a predominant thing unless you get over a couple of thousand feet, and then give us a call. We'll discuss it with you, but this is really not the phenomenon with reflected wave at the 200 volt level. At 400 and 500 or 400 and 600 volt, that is an issue. The larger in duty motors, they have usually have a blower on them to provide the extra cooling that you need at low speeds. And remember, MG1 strongly suggests that you need both bearings to be insulated on the load and the fan end, and you really need the grounding shaft also. That's a requirement with the MG1 motors at the higher horsepower, 500 frame and above. Next slide. Here's just an illustration. We're going to switch gears here a little bit again, and we're going to go back to capacitive currents. So as those capacitive currents come down the cabling, whatever you have, they're going to be introduced into the junction box, and they are going to circulate through the grease in the bearings onto the shaft, and then out the other end. Once again, these capacitive currents are seeking the drive where it was generated from. When you rectify off the distribution of 460 volts and you put it on a DC bus, you've now separated from that operating system or that distribution system. So now all the currents have to cancel to zero, and that happens at the DC bus. Next slide. Excuse me, the next, yes, thank you. What we do, it helps to put insulated bearings in here to stop this circulation. And what we want is the paint removed down at the junction box. We want a good, strong bond between the motor and directly back to the ground screw on the heatsink or the chassis of the drive. Taking all the currents back and getting them to all cancel out at 0. This is a great way to do it. We don't want the circulation through the shaft and the bearings because obviously from the slide you've seen before, it causes some significant damage. Next slide. Different types of systems. Some may still see that they might have on the very top, that's a sleeve bearing or a babbitt, whichever way you call it. I've poured a few of those myself, chuckle. But it has high stiction. I'm sure everybody aware that uses it. It was predominantly used in at the turn of the century. And then of course with the ball bearing, the advent of the ball bearing and the roller bearing, this sort of eliminated the need for babbitts. And ball bearings, you will see they have the lower anti-friction versus some of the other styles, obviously, right? Like above. The other thing too is these are used predominantly on smaller motors, and they work really well. But if you have an application on a smaller motor where you have a belt or even a chain where it cantilevers over, the roller bearing style is definitely the thing that you want to use. It will stop any premature bearing failure that you have. Next slide. I just want to touch on this a little bit. Inside your plant, obviously you probably have a person that is very concerned about power quality. Voltage imbalances. What you can see here by this chart that there's a derating factor for imbalances. So if you have single phase transformers off 2 legs of your 3-phase and you've added too many to one of the 2 phases that you have in your 3-phase, and you have imbalance between 1 and 2 and 2 and 3 and 1 and 3 to grab your single phase loads, these are going to cause a lot of imbalances. And a small voltage imbalance, and this is all I want to do, this is a very wordy slide. If you have a small voltage imbalance, it's going to be a much greater current imbalance. This will damage motors. And you can see that, you have to derate the motor due to the imbalance because you haven't got the balanced voltage for all the pulses that go through the winding. You say, well, I'll put a drive in front of it. That'll take care of everything. It won't hurt the motor any. I'll be all set. Well, it also damages motors. So it's very, very critical that you address the issues with your voltage unbalance in your plant, rebalance your single phase loads, and that will cause a lot of serious problems mechanically and electrically with your motor driven processes. Next slide.
So it's time for polling question number 3, and I believe this is also our last polling question. The question is, reflecting on today's webinar, please tell us about yourself.
Lauren, is that your last polling question for good? I hope not.
So I'll give everybody a couple more seconds to get those votes in. And I've ended the poll and I've shared the results, Kevin and Scott.
That's really kind of where I expected to see that one come in.
Yeah, that's where I thought too.
We certainly hope you feel you're getting educated from this and so forth. Let's see here. All right. Takeaways from today's webinar. First and foremost, hope you noted that properly selected motors will give you improved performance and much longer life. And the NEMA MG1 will help protect your investment. When you do a VFD motor and drive and the cabling and whatever filtering you need and all that stuff, it's a lot of money. And having the motor be correctly insulated for all of this will protect your investment because obviously these things are pretty expensive. If you've got something that you're looking for premium efficiency, consider using one of those new motor technologies that Scott went through. And how you want to do that, feel free to give us, either Scott or me, a call, and we'll be happy to help you. Make certain your motor has the correct bearings for the application. It's ball or roller, and of course roller is for when, largely is going to be when you have a belt drive on there. Belt, we don't see a lot of chain drives off the motors anymore. We see typically timing belts, and there's a fair amount of tension put on those belts, and that is reflected directly to the bearing on the output of the motor. And also whether you should have insulated bearings on your motor itself. And again, Scott and I are here to help you with that. And needs to be said that proper grounding and bonding and proper VFD cable selection is all a part of a well-designed system, in addition to the motor and VFD, which gives me a little bit of a segue here into this. There are a lot of on-demand webinars. Every single one of our webinars that we've done, including, this is Scott and my fourth one, are all available for you to come to our website, horizonsolutions.com, and up on the toolbar, you'll see a resources tab. You click on that and go to webinars, and you can see what is upcoming. And you also can go in and get our on-demand webinars and be able to watch them whenever you want. And that's how you get there. And it's not just ours, but it's every webinar that Horizon has produced.
Well, thank you, Kevin and Scott. Another great webinar. We did have some questions come in during the presentation that I'll get into now. Just a reminder to everybody that you can use the Q&A feature at the bottom of your screen to ask any questions you may have. And the first question that we have today is, how do I prevent issues with hardware overcurrents and ground faults with drives?
Kevin, you want to answer that, or do you want me to answer that?
Well, it comes back to what the last slide actually said. Grounding and bonding is everything. If you've got a VFD cable on there, you've got your VFD, you've got your motor all set up, but you don't have a proper grounding path and it's not bonded correctly, the issues are still going to be there, and you're still going to have those issues. So, it's a little bit more difficult to go back to what's in your plant already and fix this, but certainly moving forward, you want to make sure your system is properly grounded and bonded. It's not just hardware; it's how the execution is done when the system is installed.
Yes, I totally agree with that. Just remember, you're trying to prevent, with like a hardware overcurrent, is 250% instantaneous demand of the drive rating itself. So a software overcurrent would be 200%. You're definitely approaching the ground fault situation. So you want to try to prevent anything that's drawing a significant amount of current. You want to make sure that your lead lengths, right, are addressed, whether it be by the cabling situation. But Kevin is right. You really need to have a good ground reference on your drive and your motor frame, and that's how it's judging. That's its base point, where it's judging that 250%. So look for things. Look for things where you might be not using flying start, or things that would jump the current way up. Those are alarming to the processor inside the drive.
A second question that we have is, we occasionally get over voltage alarms. What causes this?
Over voltage alarms are usually caused in two different ways. If you have a bump that may come in on the distribution, maybe you're switching capacitors to increase your VAR on your network for your power factor displacement. Those bumps, when those capacitor banks pulls in, will hit the rectifier, or the bridge it's called, on the drive, and cause the elevation on the bus voltage. Remember, the bus voltage is 1.41 times the nominal power coming in, so it's even more amplified when that bump comes in from the incoming. But the other phenomenon that happens, which is more prevalent, is when the motor becomes a generator. So you have a load that's basically overhauling the motor, and it's actually generating back up to the drive. This will elevate the bus voltage. One thing that you can do that's very, very important is you need to turn on your bus regulator. The bus regulator has two actions that it can do. One is it can dump it to a resistor and provide a little more braking torque, and also dissipate the energy from the DC bus. When the DC bus gets to a certain level, it switches on and puts the resistor in the circuit and burns off the additional energy that would cause the overvoltage. The other one is, and this is what a lot of people with our 750 drives, right, is you can actually set the bus regulator to bump the frequency up. So if your process can take bumping the frequency up a little bit and causing the current to go back down to the motor and not come up into the drive, that will prevent it also. And the 750 drive will let you do the combination of both, the resistor or the increase in frequency, to prevent the bus voltage from tripping out the drive. That's a great question. Always remember, a motor can be a motor or it can be a generator.
Thanks, Scott. Somebody else would like to know, is a bus regulator a standard part of VFDs?
Yes, it is. They're in all our drives. They come in different degrees, though. The 750 is our premier flagship drive. That comes with a lot more options. You have to put in a lot of characteristics of the resistor itself so that it can actually be a higher performer. With the 525s, they are what they are. They're basically a great general purpose drive, but you can only really enable the bus regulator and turn it on. And it just sort of has a generic, I'm evaluating the bus voltage, it's too high, and I'm going to dump it to the resistor.
Somebody else would like to know, what is CIV?
CIV. Yes, Corona. Go ahead, Kevin.
That is Corona inception voltage. That is the voltage that in our case, the discussion here today, the motor windings, that's the voltage it needs to get to for Corona to happen. Now, Corona can be cool to watch, but it's not very pleasant to have happen on your plant floor. And what happens is when you exceed it, you could burn out the insulation in the windings of the motor. As we showed in that slide, there's a hole in it. And at that point now, you're going to have face-to-face shorts, and all sorts of things going to go wrong, and the motor's going to die. But Corona inception voltage is the voltage that motor, in our case today, will cause. That is the voltage at which the motor will experience a Corona event.
The other thing too is you may start to see those hardware overcurrents taking place as the Corona has affected the insulation on the windings. So if you get more and more and more of them, you're starting to get a Corona effect either on the down at the cable, maybe down near the motor junction box, or in the first end turns of the motor. So very, very important to keep an eye on those. That's why we have you cycle power to a hardware overcurrent or to a ground fault. We want you to recognize how serious this is and that it needs to be addressed.
Thank you. I think this is going to have to be our last question for today, but everybody can always contact Scott and Kevin at their contact information on the screen there if you have any lingering questions. Our last question is, do brake IGBT have similar function as brake resistor?
That's a good question.
Go ahead, Kevin. They work together. But if you don't have the brake IGBT, you have no way for the drive to send that regenerated energy out to the braking resistor. So it is something that you have to have in the drive, and it's something that you get in the drive from the factory. And that is what actually sends that regenerated energy off the DC bus out to the braking resistor. So while they don't do the same thing, you got to have one with the other.
And one really quick example of, does it apply for the brake transistor as well as the supply transistors? Imagine if you had a generator a long distance away and you had a regen drive that would be able to, generate the power back up onto a pole. Imagine you had to break the generator because you need to do maintenance off it and pull it out of a body of water. Those lead links and that IGBT still have the same properties, and you must be aware the reflected wave could cause an issue. So once again, you need to evaluate the CIV on the windings of the generator, because you are truly just only using the braking transistor, right, for the system, right? But you have to take into account it's the same devices, the same distances, and the same phenomenons happen. So just keep that in mind. That's a really good question.
Thank you, guys, and thank you for everyone who joined us today. We have concluded the Q&A portion of the webinar, and please consider joining us on our following webinars. Kevin, I believe the next slide might have the upcoming ones. Yes, the next upcoming webinar is the 29th. Chris Williams will be discussing how to size a servo system, and then following him on 11-12 and 12-17 is why smart sensing is the key to smart manufacturing and how to configure static switches. So I hope you all can join us then. Do you guys have any closing remarks you'd like to make?
Well, I certainly do. For Scott and I, this is our fourth and final webinar of 2020. We really appreciate everybody participating in this and coming and joining us here. There's a tremendous amount of work that goes into these things, right, starting with conceptualizing what we're going to do and how we're going to lay it out, gathering all the information, whether it be data or images or whatever it is, getting permission to use these images, and then putting it all together, building this presentation, rehearsing it. Scott and I have rehearsed this many times, and I personally have run through this thing because it's actually running on my computer. I've run through this at least 25 times myself just to make sure all the animation works and so forth. It's a lot of work, and seeing as many people come and participate and watch this makes it all worthwhile, because I know it's we're all very busy, and it really is gratifying to know that you've taken the time to come out and watch these, and we do truly appreciate that.
I just hope everybody stays safe out there. We definitely miss face-to-face with customers that right now are not accepting us to come in and be used as a technical resource. We're always here for you. This is one way that we do it through these webinars. Don't forget about our blogs. We write a lot of blogs on the Horizon Solution website that you can get a lot of great technical information from. So even though we're going through this period of time, just always remember we're there for you, and we really, really appreciate your business, and thank you so much.